Center in Yorktown Heights. And it was a filmmaker that directed this documentary called Particle Fever that I don't know if you've had a chance to watch, but I highly recommend it. It's about the team that was pursuing the discovery of the Higgs boson in the largest physics experiment ever conducted. And a major character in the film is a professor from Stanford. And at the beginning of the film, he said something that really captivated me. He said, the thing that differentiates scientists is a purely artistic ability to discern what is a good idea, what is a beautiful idea, what is worth spending time on, and most importantly, what is a problem that is sufficiently interesting, yet sufficiently difficult that it hasn't yet been solved, but the time for solving it has come now. So I want to tell you about this beautiful idea whose time for solving it has come now. And that is the possibility to create quantum computers. If you look at how we have created the basis of the information revolution, and you trace it back to other beautiful ideas, like what Shannon taught us, to think about the world of information abstractly. If you look at, an old punch card and DNA, we've come to appreciate that both carry something in common. They carry information. And Shannon told us that this world of bits could be decoupled from its physical implementation. That was really interesting, but in fundamental ways, it went too far, leaving too much physics out. So here is two scientists that work at IBM Research. Charlie Bennett on the right continues to work in our laboratory and is an IBM fellow. And they asked the question at the time of, is there a fundamental limit to how efficient number crunching can be, computing can be? And when they asked that question as physicists, they ended up with a very surprising answer. And they found the answer to be no. It turns out that number crunching can be thermodynamically reversible. This led to an exploration of what is the relationship between physics and information. And there was a now famous conference that was jointly organized between IBM Research and MIT at Endicott House, where this topic was explored in more detail, and the plenary speaker was none other than Richard Feynman. And Feynman proposed in that conference that if we wanted to simulate nature, we should build a quantum computer. And I'm going to explain you what that means and how it's created and the problems that it will solve. But first, I got to tell you what is the fundamental idea. The fundamental idea, just like we have bits in the classical world that can be a 0 or a 1, in a quantum computer, you have qubits, which stands for quantum bits. Now, the difference is that they can be a 0, a 1, or both at the same time. That exploits a principle of quantum physics called superposition. And it sounds weird and crazy, but it's true. Now, to give you this unease that you should feel when you talk about quantum information and quantum computing, I'm going to give you a very simple example, a thought experiment that also happens to be true. So let's imagine that we're going to solve this problem. The problem involves you have 4 cards. 3 are identical, 1 is different, 1 is a queen. We shuffle the cards and we put them face down, and the problem we're going to solve together is find the queen. We're going to be assisted by 2 computers. 1 is a classical computer, 1 is a quantum computer. So what we do is we turn them down and we load them into memory. So we use 4 memory slots. The cards are identical, we put zeros. The one that has a queen, we put a 1, right? So in our 4 slots, we'll have 3 zeros and 1 is a 1. We load them on the 2 computers. Now we ask to write a program to find the queen, find the 1. How would it be done classically? You would go and pick a random number, you don't know where it is. You go, look under that memory slot, see if it's a 1. If not, you go to the next slot, and so on and so on. On average, it would take you the equivalent of 2.5 turns to find it. It turns out that with a 2-qubit quantum computer for this problem, you can always solve it in one shot. So that uneasy feeling that you have now should be an explanation that quantum computer is not just about building a faster computer, it is building something that is fundamentally different than a classical computer. Now, a way to think about it, an abstraction of it, is that a quantum computer is always going to have a classical computer next to it. They have to go together. So you have a classical set of bits, right? The problem that you're trying to explore. And what the quantum computer is going to allow you to do is to explore this exponential number of states, this 2 to the n, where n is the number of qubits that you have. So now we have relatively small quantum computers with few qubits, but just think of the number that by the time you have 50 qubits, you have 2 to the 50 states. That's a phenomenally large number. But in the end, after you explore this number of states, you go back to a classical output, a string of zeros and ones that you interpret with a normal computer. So why is this interesting? And I think in this audience, I don't need to, explain in great detail, what exponentials mean and why 2 to the 50 is a very large number. But it's still, I think it's an interesting way to communicate the power of this, and I'd like to map it to some problems. But I like to go after this apocryphal story that actually IBM used in the 1960s to explain to people the power of exponentials. And it had to do with the person who invented chess that goes to the emperor and says, well, here's this wonderful game, and asks, what do you want in return? And the person who invented it is, give me a grain of rice on the first day for the first square, and the second day, you give me twice as much, and on the third day, you give me, twice as much as the day before. And the emperor agrees promptly that that seems quite reasonable. And after a week, you only have 127 grains. After a month, you have more rice than you'll eat in your lifetime for sure. But just by the time you get to the end of the chessboard, you have more rice than Mount Everest. So there are a large number of problems in the world that have this characteristic that they blow up exponentially. And a dirty secret in the world of computing is that we obviously talk a lot about all the things that computers can solve, and can solve a lot of things, but then there is a lot of things that computers cannot solve. And very interestingly, they cannot solve it now, nor ever. And the reason is because they have this exponential built into them. So take as an example this fairly simple equation, factoring. So if I have a number m that is made out of the multiplication of two large prime numbers, and I only give you m, and I ask you, find me p and q, it turns out that that is phenomenally difficult to solve. There's no other way but to divide it sort of sequentially by prime numbers. So, in fact, it's so difficult, we use it as the basis of all encryption. But if you had a very large universal fault-tolerant quantum computer, which is many, many years away, you could solve that problem in seconds, what would take billions of years in a classical computer. That tells you something about the power of what is going to be possible. Take chemistry as a problem, because it also has this characteristic that it blows up exponentially if you try to calculate it. This equation that you see here is very interesting because it's predicted to occur at the ocean floor near volcanic sites, and famously it's been hypothesized to be the basis of the formation of life on Earth. But if you take a molecule like iron sulfide and you try to do relatively simple calculations with a normal machine, it turns out that we're not very accurate. And the reason is that molecules form when electron orbitals overlap, and the calculation of each orbital requires a quantum mechanical calculation. So for that simple molecule, you have on the order of 76 orbitals, and 2 to the power of 76 is intractable with a classical computer, so we cannot solve it. Again, on this theme of or assumptions that computers solve everything, but they don't, if you look at calculating, for example, the bond length of a simple molecule like calcium monofluoride, we still get it off by a factor of 2, even using the larger supercomputers in the world. To me, this has been very interesting, this recognition of all these problems we cannot solve. It's also true in optimization problems. They are the basis of logistics and routing and, portfolio optimization. There's tons and tons of problems in which at best we do approximations, but we're far from optimal because the number of possibilities is enormous. So if there's one message I want to be able to come across is that we have these easy problems, which is the world where classical computers fit and the problems it solves. But then there's these other hard problems that go outside. And if you don't believe that P equals NP, which I would say the majority of mathematicians don't believe that that is the case, that those problems are hard for a reason, the only avenue to go and tackle that, aside from approximations, will be through the creation of quantum computers. So where are we? We believe that small practical quantum computers are going to be possible, and we're building them now. It requires reinventing the whole stack. The device is different. It's not the traditional transistors. As an example, this is the device we use for the quantum computers that we create at IBM based on superconducting Josephson junctions. And you're seeing an example of one of these devices. It's a superconducting device. And because it's superconducting, you have to cool it. So this is what a small quantum computer looks like. What you're seeing here is something called a dilution refrigerator. And this quantum processor sits at the bottom of this refrigerator at the nice temperature of 15 millikelvin. So that is colder than outer space, where we have to put this quantum processor in. This is what, for example, a 16-qubit quantum processor looks like. And, inside you see the square where the qubits are, and you see these squiggly lines, which is these coupling resonators that allow you to send the information and couple to the qubits to send the information. This is what the wiring looks like into the refrigerator going into a quantum processor. Is these coaxial cables, and because the way you send information to a quantum processor is through a series of microwave pulses that go in, and then you're able to take it out. Now, if you look at pictures of what computers were like, right, in the 40s and the 50s, it's kind of like where we are today, right? That's what, quantum computer, that's the signal processing required to actually send all those signals down the coaxial cables. It looks like that. But we've also seen this movie before, in the sense that we know how much progress we have made from those early systems. And while we don't anticipate that quantum computers will be on your phone, because they require cryogenic cooling, we definitely believe that access to quantum computers in the cloud will be something that people will be able to leverage behind the scenes, even not knowing. Because we believe that, we created a small quantum computer last year, and we made it available to the world, and something called the IBM Quantum Experience. And all of you can go and log in and have access to this. It's available for free. It's a 5-qubit machine. And since we launched it, we have over 36,000 users from over 100 countries that have been doing it. And 15 scientific publications have gone on it, and people are learning how to program and to learn about this new world and what is being created. And you can actually run things on this. So I was telling you about these chemistry problems. So this is an example of the expected theoretical calculation and the actual calculation on a small quantum machine of hydrogen. So we're starting to solve small problems, and what is coming in the years ahead, in the next few years, will be machines that no classical computer will be able to emulate. Because by the time you have order of 50 qubits, think about that, that's 2 to the 50 states. And no classical machine will be able to emulate what that can do. And that is new territory, and that's the territory we're all going to enter. And now is the most interesting part, because it'll be the path of discovery of what we can do and what value we can create on problems we couldn't solve before. So I'll close with Feynman, who proposed this original idea of creating these quantum machines. And his, inimitable style, he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, is a wonderful problem of creating these quantum machines. And his, inimitable style, he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. Of creating these quantum machines. And his, inimitable style, he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. Of creating these quantum machines. And his, inimitable style, he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical.
Number, mind-bogglingly large number of parallel realities, as real as this one, that have different consistent histories. So imagine a world where all of the laws of physics as we know them are obeyed, but different decisions were made along the way. Different decisions at the level of tiny microscopic particles, different decisions all the way up to what you chose to eat for lunch, and whether you chose to come to the session or not. Quantum mechanics makes a very specific prediction that all of those are as real as the thing that you remember. And this is bizarre, because we don't see those other things. But science has reached the point now where we can build machines that exploit those other worlds. And quantum computers are perhaps the most exciting of all of these that we have within, or almost within our grasp right now. So people from a physics background love this. They want to understand the world. They want to understand the universe, how it all works. There's another type of person who tends to come from the computer science side that's like, yeah, okay, that's all great. But there's a different thing going on here, which is just as exciting, if not more, and that these machines that supposedly can do this wild stuff, let's forget about how they work, if you could build one, could solve problems that you could never, ever solve with any computer of the sort that we built. If you took every single atom of silicon in the world and made the most sophisticated conventional Intel-style processor that you could build, there are problems we know of that I could write down on a sheet of paper that you could never, ever, ever solve with that thing, that you could with this kind of machine. So that's very exciting. Humans use tools to do things. If you give humans a new kind of tool that can do things that you couldn't otherwise do, imagine the possibilities. So you may think, well, this is all fine and dandy, but aren't these things in the realm of theory and speculation kind of in the same regime as other futuristic things you may have heard of which may be allowed by the laws of physics but aren't here yet? That's not true. There are in fact many of these machines deployed now in openly available research centers following the model that was used to introduce supercomputers to the world. They're too big and ornery and difficult to operate to put in your home, too expensive also, but you can give them to a place which will manage them as a shared resource that will offer that service to the world. And there are two of these now. One of them is at the University of Southern California. And this analogy with flight, I think, is an interesting one. So a horse can beat, or could beat, the initial flight of the Wright brothers' flight in speed. But a plane is not a faster horse. A plane is a different kind of machine. The plane takes advantage of another resource that nature gives us, this third dimension, in order to do something that matters to people better that you could do with any horse. It doesn't matter how fast you make a horse, it will never fly, at least the kinds of horses that we know about. So these types of computers now are being thought of in the same way. They're not terrifically powerful yet, but they're doing something completely different than what your computer does. And that thing is like flight. It gives these computers access to these new resources, maybe you could call them parallel universes, in order to do something that you couldn't otherwise do. And that's not the only one. In fact, the one I'm going to come back to and talk to in the context of the story that I'm wrapping this in was recently installed at NASA. And Google was the primary interested party that pulled this whole thing together. And this one is really exciting to me, because what they're going to do is apply this machine to an area that I think is fundamentally important. It's the crux of our future as humans, and that's, can we build machines like us? So, building machines like us might be possible. I certainly believe it is. I might be wrong. But what I do know is that the types of approaches that people are taking now to build intelligent machines benefit immensely from what this machine that we've built does best. So what this center is about is applying this beautiful new computational idea in the service of trying to make intelligent machines. Now, I can't think of anything personally any cooler than trying to use quantum computers to build intelligent machines, so this is very exciting to me. Steve Jurvetson has been a longtime friend and investor in the company, and for those of you who don't know him, he's a Silicon Valley investor who's probably the smartest VC that I know of, and certainly the one that's the most attuned to technological trends. He's on the board of SpaceX, Tesla, Synthetic Genomics, which is Craig Venter's company, is trying to build artificial life, and D-Wave, and that's it. And this is his particularly poetic way of framing the difference between the machines we build and conventional computers. This is what they look like. There are two of them. These are from our lab in Burnaby in British Columbia. From the outside, they look like giant black monoliths, big metal boxes, about 10 feet on a side, 12 feet tall. And they are powered, they have a fridge inside them, a refrigerator that cools these chips to almost absolute zero. Just a wisp, a fraction of a degree above absolute zero. Hundreds of times colder than interstellar space. Amongst the coldest and most isolated and extreme conditions that humans have ever been able to engineer. These fridges, interestingly enough, which are called pulse tube dilution refrigerators, have a thing called a pulse tube, which emits a sound roughly once per second, which sounds eerily like a heartbeat. So if you have the opportunity to stand next to one of these machines, it is an awe-inspiring thing, at least for me. It feels like an altar to an alien god. They really are impressive machines. At the heart of this big box is a tiny chip about the size of your thumbnail. And on this chip resides all of the wonder and magic that makes this thing go. I'm not going to describe in any mathematical detail how it all works, but let me give you an analogy. In quantum mechanics, there's this concept that a thing can exist in two states which are mutually exclusive at the same time, quote unquote. So I'm using those words because the English language was developed before we had concepts to describe what these things actually are doing. But I'm going to give you a roundabout way of understanding this. Imagine that there really are parallel universes out there, and now imagine you have two that are exactly identical in every respect, all the way out to the horizon as far as we can see, down to the last little atomic detail of every single thing, with only one difference. And that's the value of a little thing called a qubit on this chip, which is the contraction of quantum bit. And that qubit is very much like a bit or a transistor in a conventional computer. It has two distinct physical states, which we call 0 and 1 for bit. In a conventional computer, these are mutually exclusive. That device is either one or the other, and never anything else. In a quantum computer, that device can be in this strange situation where these two parallel universes have a nexus, a point in space where they overlap. And when you increase the number of these devices, every time you add one of these qubits, you double the number of these parallel universes that you have access to, until such time when you get to a chip like this, which is about 500 of these bits, you have something like 2 to the 500th power of these guys living in that chip. So the way I think about it is that the shadows of these parallel worlds overlap with ours. And if we're smart enough, we can dive into them and grab their resources and pull them back into ours to make an effect in our world. Now, this may sound very odd to you and bizarre, and in fact, I am using language that a normal theoretical physicist probably wouldn't use, but this is, what I'm telling you is absolutely correct and in line with the way that these things actually work. We've been doing this for some time now, and in fact, we have our own version of Moore's Law. The doubling of the number of these qubits on the chip has happened once a year for the past 9 years. So for the last 9 years, every year the number of these qubit devices has doubled, and it will continue to do so. As a point of reference in terms of how fast these things are, in one generation of chip, the one from the system that was installed at USC to the one that Google and NASA have now, the speed of the device went up by almost 500,000. This is the kind of progress that you're going to see with these types of machines going forward. And 500,000 sounds like an abstract number, but I put up a little mental comparison here to see what 5,000 really means. 500,000 is a big number when it comes to speed. All right, so now I'm getting into the last part of my talk where I'm going to make some predictions, some dangerous predictions. So predictions are very dangerous for a variety of reasons. Often they're wrong, which is one. But I think they're important because predictions somehow are our internal desires made manifest. Predictions are about what we want to happen, maybe not what will happen. And I'm going to make 3 predictions, and all of them are dangerous in the sense that they're very unlikely to happen, maybe, but I think that there's a very good chance that they may. As an aside, I just wanted to say that at least in the Valley, Silicon Valley, and maybe in the United States in general, there's a very deep feeling of unease about the way technology has been developing. Because we have all of these vast array of very smart people, and what they're doing is crap. They're building things that cannot last. They're building things that are not important. This is a little bit of a controversial point of view, but I believe it. But I think that the reason for this is it's low-hanging fruit. Computers haven't been around for a long time. And I think that what's going to happen is that as people get more comfortable with computers, the attention will turn from the Twitters and the Facebooks to very important things. So here's my first prediction. I'm going to predict that by 5 years, NASA will have found an Earth-like planet with Earth-like atmosphere and water on it, and serious people will start discussing how we get there. And by the way, they're going to use one of our machines to help do this. So that's my first prediction. My second prediction is that this business of parallel universes is going to turn out to be very important. This picture that I've got under here is what's called a gravitational lens. When Einstein proposed his general theory of relativity, it came with a bunch of experiments that you could use to test it. And one of them was that if there was a point of light very far away and a galaxy in the middle, that galaxy should bend the light and you should see a ring. And this was eventually observed. And I think what's going to happen is somebody is going to come up with an experiment to test this reality of these things. And we're going to be able to do so. My third prediction that I'm going to end on is the most important of all. I believe that humanity is on the cusp of the most important technological, societal revolution that's ever occurred. And that's when we got to the point where the machines that we build outpace us in every respect. I don't mean that they're better calculators. I don't mean that they're better at searching. I mean everything. And I think that we're very close. And my prediction is that within 15 years, we will have machines that outpace humans in everything. Thank you very much.
If you manage a team, you should be using Monday.